Thank you very much, Strato, for the introduction. Thank you for the invitation. It's great to be here. In fact, it's the second time over the past 12 months. I recognize some of the people here who made it to my seminar last year. The title is the same, but there's going to be some new results, so bear with me during the presentation. So I'm going to talk about certain things happening at the interface between computer science and operations research, machine learning and optimization. Of course, there's a great deal of things happening in that domain nowadays. Just like in every domain in science and engineering, there's so much influx of machine learning, AI techniques. The same thing is happening in optimization, where, of course, on the one hand, you have computer scientists rediscovering some very old optimization algorithms like steepest descent that they are now using to train these complex neural networks. But in fairness, CS folks have actually brought quite a bit into the field of optimization. Not only did they rediscover these optimization algorithms, but they actually came up with new versions. They improved them so that these algorithms are now, for the first time, able to run on very large data sets and so on and so forth. And there, of course, there's a lot of excitement now by application people, practitioners who are now using AI and ML in all kinds of applications. So I'm going to talk about 3 software projects, if you wish, the Baron project, the Alamo, and the BAM project. They all have to do with solving some optimization problems. The first has to do with optimization problems for which we have an algebraic model. Then the second has to do with optimization problems for which we don't quite have an algebraic model, but we can build one from measurements. And we'll talk about an algorithm for building models from data. And finally, I will actually optimize on top of black boxes. So I'm going to go gradually from algebraic to algebraic plus some black box, and then to eventually entirely a black box, and explain why we look at these problems, how we actually combine some elements of machine learning to make things work out, and how we solve problems at the end. So very quick introduction to optimization. It's not a new field, and some might say, oh, it started with the Greeks. Well, it didn't quite start with the Greeks like other fields. It was not until people like Newton started putting things together. Of course, calculus had a lot to do with where we stand in terms of optimization nowadays. Interestingly, Newton, we should credit him not just for the development of optimization algorithms, but for what we might call the first machine learning algorithm. He developed least squares in an effort to figure out, to predict basically the position of a lost asteroid. And he did it utilizing a model that somebody else had proposed from first principles. So it's interesting that he's doing not just building models out of data, but models that somehow fit physics. So it's interesting to mention. And then in the context of what is going on in other application areas like chemistry, physics, folks figured out that once optimization models were put in place, they can be actually applied to, say, predict equilibria, predict structures of molecules and so forth. Unfortunately, these are very hard problems from the optimization point of view. Yes, from the theoretical point of view, these problems can be posed. Certain problems can be posed as optimization formulations, but they're very hard to solve. Okay? So when optimization actually really comes into applications is back during the war, when people figured out how to use optimization problems with linear objectives, linear constraints to do logistics types of problems for the Air Force and so forth. And then the chemical process industry says linearity is great. We can solve linear optimization problems, but they don't quite apply to chemical processes that much. Chemical processes, reactors, and the likes, they're non-linear. So we have to figure out how to solve optimization problems with nonlinearities. Okay. And then the airlines came and said, if I am to assign an aircraft to a route, I have to assign exactly one aircraft. I cannot do 1/2 or 3/4. So they forced us to think in terms of integer variables, in integer optimization. And now what's happening nowadays is, of course, we are now at the next stage, which is optimization problems that involve a mixture of integer and continuous variables, as well as nonlinearity, so these MI-NLPs. And of course, we do machine learning, okay, in various ways. And all I'm saying here, for those who understand Greek, is that machine learning is not perfect, okay? The translations we get out there, they may not be entirely perfect, but they're definitely of great use in many fields. And in fact, in terms of your spam filter, yes, it's not perfect, but the error rate there is much lower than mine and my secretary's combined. So it's a great deal. What's happening in machine learning nowadays is very interesting. Not perfect, but many tools in ML, AI in general are being used now to solve MI-NLPs and other types of optimization problems. All right, so the problem I'm primarily interested in says I want to solve some optimization problem. It's nonlinear, so if you think in terms of the objective function, it's not straight line, so it's nonlinear, as I'm showing here. This is my independent variable, this is the objective function. And more than that, I'm interested in problems that are multimodal. So I have multiple hills and valleys. Again, not a new problem. People have been looking at it for a long time. Classical optimization, start at the starting point, move downhill until you find a point where the gradient is 0. And you might miss, of course, the global solution, which in some cases may not be that important, but in other cases, say in Gibbs free energy minimization, I have to go to global minimum, okay? And of course, in practice, I would like to minimize costs as much as I can. I would like to go to a global maximum, a global profit, and so on and so forth. So that's the problem I'm interested in. And I'm going to start by looking at the case in which I have this function available in algebraic format, maybe some constraints also available in algebraic format, and I'll see what it is I can do to solve this problem. So there's this algorithm called branch and bound that says, well, if I can somehow construct what we call a relaxation, another optimization problem that is such that it doesn't have multiple local optima, just a unique local minimum here. And it is such that its objective function underestimates the original problem everywhere in the domain of interest. What I can do now, I can use a standard optimization algorithm, start from any starting point, move down here until I get the 0 gradient point. I will be able to get a lower bound for the global optimum, okay, for the global minimum. And then what I can do some local sets with any standard optimization algorithm. In this case, I took the relaxed problem solution, I used it as a starting point, and I moved downhill. At that point, I will get an upper bound for the global optimum. Okay? So it happens here, I'm lucky, I'm getting the best solution possible, but in general, all I get is an upper bound. And then what this algorithm says, well, if this range here is small enough, we have a proof of optimality, we can declare victory. If that range is not small enough for you, then the algorithm says, I'm going to partition now the set space into subsets and repeat this process of lower bounding with relaxations. So that's what I've done here. I have 2 subsets, one to the right, one to the left of the relaxation solution. Over each subset, I construct now new relaxations. And now the lower bound is going to be the list of the 2 lower bounds. So as we can see now, my new lower bound is considerably improved in comparison to what I started with. And again, if this range here is small enough, we are done. If it's not small enough, we will have to keep on. My computer decided it's time to do my daily backup. I'm sorry. Right, so if this range now is not small enough, the cool thing is, if you pay close attention here, the lower bound for region 2 is already above the upper bound that I have for the problem. It's above the best solution node. So that means I can eliminate region 2 from further consideration with an optimality argument. There's no need to look further into that region. So branch and bound is basically a way to divide and conquer. That's what we're doing here. And you can map all this into a branch and bound tree where nodes correspond to solving relaxations and branches in the tree correspond to partitioning the set space into smaller subsets. Now this is going to work provided I can build these relaxations somehow. And that's where the name of the game is. How do I do this mathematically, rigorously? That's where we expend a lot of energy in this field. So one way for doing this is to take any function of interest, function for which I would like to construct a relaxation, an underestimator, introduce many intermediate variables. The way you would go about computing this for the old timers, you know about Polish notation or that kind of stuff. So I'm introducing variables for intermediate quantities I would need to compute to calculate this function. And now the problem of underestimating the original function is equivalent to outer approximating this set of equations. The good thing here is if you look at this set of equations, what we have is expressions that are basically mostly, for the most, univariate. So if I look at this expression, for instance, I'm looking at the logarithm. We know what the logarithm looks like. It's a concave function. Looking at the exponential, again, it's a convex function. We know what these things look like. If needed, we can just plot them, figure it out. We can, of course, do some systematic analysis based on looking at gradients of functions and so forth. But the important thing is, for univariate functions, it's easy to build underestimators. Think of a function like negative x squared, a concave function of a region. Hey, the secant joining the two endpoints of that function does provide an underestimator. I left the bilinear terms because people have analyzed this function as well. It's in 2D. They figured out how to build the tightest possible convex relaxations for this function as well. So at the end, you take all those things together and you can build an outer approximation for the original function as well. So I'm just giving you some idea about how these things are being done, not going through all details. But in general, I have these nonlinear functions in red, multimodal. I would like to build convex underestimators and concave overestimators. If you can build the tightest possible ones that I'm showing here, the envelopes, that will then expedite this branch and bound algorithm because the quality of the lower bounds is going to be better. The lower bounds will be much closer to your upper bounds. And all I'm saying here in this figure is in some cases, like in the concave case, the concave function, the convex envelope is obtained once I know the function values at the two endpoints. The same goes with this case here. Even though I have multiple local minima, again, the generating set for the convex envelope is finite, just those two function values I need to know. The same goes here, even though I have infinitely many local minima. Again, as long as I know the function values, the finite set of points, I can generate these envelopes. That's an observation on which one can build on and then construct many convex envelopes and concave envelopes of many functions. And of course, we have many results in this context, for instance, for the ratio x over y. If you look at this function, well, it's not convex, but if you take slices, if you fix, let's say, the denominator, then you're looking at a linear function. A linear function can be viewed as a concave function, and therefore you can argue it's only the two endpoints that I need to be focusing on. So at the end of the day, you can argue the generating set for that envelope can only be along the two green line segments. Once you have that kind of intuition, then there's something called disjunctive programming that's been out there for a long time that can be utilized systematically to construct these envelopes. So it takes some effort to do this, but it can be done for many types of functions, and we've done this for many types of functions. For all these functions, for instance, this is a small subset. At the end of the day, because we have the algebraic expressions for all this, we can look at gradients, we can characterize the generating set for the envelopes, and we can use these truncated programming techniques to construct the tightest possible relaxations. And once I have this, then wherever these functions show up as parts, building blocks of more complex functions, I can utilize the envelopes and I can have a very efficient branch and bound algorithm. All right, so overall, and of course I have skipped a lot of detail here in terms of this algorithm. We can do branch and bound, not just for integer problems, but also for continuous problems. I didn't talk about convergence of this algorithm. If the space involves only integer variables, say binary variables, the set space is countable, it's finite, it's easy to claim the algorithm is finite. For continuous problems, it's not that trivial. Just take my word for it. Under certain conditions, this algorithm will be convergent at the limit. As iterations increase, that lower bound will asymptotically approach the global minimum. Okay. In some cases, you can make the algorithm finite even for continuous problems, and that helps. In terms of relaxations, we're using these convex concave envelopes, typically referred to as McCormick's relaxation in the literature. But we also go further and we recognize convexity. There's ways to do this systematically. We even recognize convex transformability. In the context of neural networks nowadays that many people care about, those sigmoidal functions, hey, we can actually exploit the fact that they can be convexified after transformation, and then that helps improve lower bounds. Then, yes, we do use envelopes, as I mentioned earlier, for certain types of functions. And then we go further and say, even when we have nonlinear relaxations like the red one here, if I'm to solve that relaxation, I need to rely on nonlinear programming technology, which is not as robust as linear programming technology. So oftentimes we will go there and we will systematically out-approximate nonlinear relaxations by polyhedral relaxations, as I'm doing here by taking supporting hyperplanes of the red function. Then we can rely on linear programming technology to solve our relaxations. That can be done way more effectively than nonlinear programming technology. You might have heard of something called cutting planes in the context of integer programming. We generate cutting planes for many types of nonlinear structures. And at the end, we rely on constraint propagation. That's something that was first developed in the AI literature in the context of doing reasoning. People figured out how to satisfy constraints. If you look at this problem here, I'm assuming I have two linear constraints in 2D. So the blue box is the initial set of bounds for the variables. But if you look closely at the constraints, if you look at one constraint, one variable at a time, you can infer the red box, which is tighter. Okay, so this inferencing here can be used to simplify the search and speed up the algorithms. And eventually, there's also results from nonlinear programming, linear programming, and nonlinear programming duality that I can rely on to do further inferencing and strengthen relaxations. You put all this together, and then you have a software. So I'm talking about the Baron solver that we started developing back in '91 when I joined Illinois. I'm showing here results for this solver over a 20-some year time period here. And I'm showing two things on a collection of problems that I don't necessarily like, but somebody else has been using up until very recently to benchmark MI-NLP solvers. The things I'm showing here on the left, I guess in green, that's percentage of problems that we are able to solve. So when we started, we had very humble beginnings. We could barely solve 1 in 3 problems. As time goes by now, at this point, we can solve almost the entire collection, 3 times as many problems as when we started. In red, I'm showing CPU time on this collection. It's now we're about 40 times faster than what we used to be when we started. So I'm running now different versions of the algorithm on the same hardware. That's how I'm doing this comparison. So there's been quite a bit of progress in this context, and things did not happen overnight. It took a long time to get here. Putting together all these pieces, different algorithmic pieces, it takes a lot of effort. And we're still, as you can see here, we're not done. We're not able to solve all the problems. Okay. In fact, Baron was the first MINLP solver to address to provide global solutions. There's been developments by the optimization community, many different solvers. Some of them can only guarantee local optima, others can guarantee global as well. And as you can see now, there's a number of solvers out there to do MINLP. There's a whole community. When we started, there was not a whole lot, but now there's nearly 30 MINLP codes out there. Just as of a couple of years ago, we now have the two largest optimization companies. Express is developed by Fair Isaac. The folks could do all these ratings. And Grobi, of course, is the largest optimization company. They just got into this field as well. I'm listing here some applications that where people actually use Baron. That's how I found all these. They're citing Baron. I look them up and I confirm. So some people are doing COVID management. Others are optimizing portfolios. People optimize refineries. I really like the idea of doing algorithm design using non-convex optimization models to sort of tune basically different types of algorithms. We can even think in terms of designing algorithms from scratch. We can model that problem as an MINLP. It's a very interesting application area. So that's what's driving the developments in MINLP. So all that works nicely as long as I have the algebraic model for the objective function and the constraints, and we can then take advantage of all the special structure in these models and solve them. We don't always have these kinds of models, so I'm going to switch now to a somewhat different problem that says, let's say you want to optimize this power plant. We have some algebraic models. We know, for instance, there's flow here. This arcs here denote flow. Whatever comes out of this unit must be the input to that unit. Some basic things we have models, but then for other cases, we may have just a black box, a simulator describing whatever is happening in that unit. And all I can do is run the simulator. I don't have an algebraic model. I can probably invest, if one of my students develop an algebraic model, it might take us a year to figure out the solution to the differential equations and everything, the proper model. It takes time. So an alternative here to developing an algebraic model would be to say, I'm going to take these simulators, run the simulators, and use as much information as I can from them to infer algebraic models. So take the large process, break it down into pieces. And if it's an aircraft, think in terms of different pieces, the wings, fuselage, and so on and so forth. You simulate each piece independently, many, many times. Collect data for each of the different blocks independently. Fit the data to your favorite machine learning model. And then take all those algebraic models, put them together into an algebraic optimization formulation that you can now solve. And there are many people looking at all this, of course, in engineering, and realizing it's very hard to optimize things if I have a neural network model in here. Very difficult. And yes, there are tailored algorithms, and we are improving what we know in that context and what we do, but it's still a very difficult problem to do. It's very difficult to optimize on top of a neural network. So that basically prompted me, when we were starting this work about 15 years ago, to think in terms of what kinds of models would be best in the context of an optimization application. And I realized pretty quickly that some very complex models are so complex that the final optimization step would be very difficult, even if they are accurate. At the other extreme, if I go for a linear fit for the data, I know that would be inaccurate, and therefore I wouldn't be able to come up with meaningful results. So we decided to stay somewhere in between. And there are things that can be done somewhere in between, like people are probably familiar with the lasso that everybody is using in machine learning. We decided to develop this Alamo approach that goes as follows. We have a black box function. This is the simulator that you want to learn from measurements. I will take some measurements, like the measurements shown here, and I would like to fit them to a model. But I don't want that model to be complex. I want it to be as simple as possible. So I'm going to postulate a collection of basis functions that can be used to describe the space. Okay? My basis functions here, well, I have a constant, I have some linear terms, bilinear interactions, maybe some exponentials. I'm using more than one basis here. I'm overdoing it in some sense, only because I want at the end of the day to come up with the simplest possible model. And in some cases, exponentials make more sense than anything else. In other cases, trigonometrics may make more sense than anything else. So bottom line is, I need to select a subset of all these terms that I will utilize. The betas here are just regression coefficients, okay? So how do we go about doing this model reduction systematically? And the answer is, those integer variables, those binary variables that the airlines forced us to think about a few, 2-3 decades ago can be very useful. I will assign a binary variable to each one of these terms, and that variable will be used to turn the term on or off, okay? At the end, I have to select a subset of the terms, and we are going to do this using information criteria like the Bayesian information criterion or Akaike's information criterion that balance sum of square residuals against complexity of the model. So they penalize the sum of binary variables that are turned, that model the selection of terms. That's a mixed QP that I can now solve with Baron, or Gurobi if you prefer, or Simplex, or any other good MINLP solver, MIQP solver. And once I do that, I have a model, which is as good as my collection of measurements, which in this particular example, I'm missing something. I haven't quite taken measurements in this part of the domain. So the next step here is to figure out where the model breaks down. And we have a systematic approach to do this by what we call adaptive sampling. People in AI, ML call active learning. We model this problem as a derivative-free optimization problem, and that's how we actually identify points where the domain, points in the domain where the kind of model breaks down, put those points in the measuring set, in the training set, and then go through the process again, build a new model until eventually you have sampled enough that all your samples are coming back saying, hey, your kind of model is modeling accurately the unknown function. And then we will take this and go off and use it for modeling of that particular block of the large system. So here's some comparisons here between what we do in Alamo and what you would get if you were instead to use ordinary regression or the lasso. Doing this on a collection of 45 problems that we synthesized. And what I'm comparing here is the number of terms in the model that we built with any of these modelers against the number of terms in the true function. So if I'm doing a good job here, this difference ought to come to be very close to 0. Of course, I have a distribution because I have 45 functions. And as you can see, with ordinary regression, you get models that sometimes are very large. We know this typically, we overfit with ordinary regression. Things don't work out very well. The lasso is doing much better, and it's known to do much better just by penalizing the magnitude of the coefficients. Essence, it penalizes complexity. And as you can see, Alamo does even better. So best subset selection does even better. In fact, the distribution here is negatively skewed, meaning we can even simplify some of those functions. Yeah? So this is kind of an interesting result. And then, of course, the next step for us was to go and say, okay, how do we do for problems that are out there? So we collected a bunch of problems for various machine learning repositories. UC, Rhine, a few others. Here I'm showing information on the sizes of these problems, not large data sets, okay? One of Alamo's limitations is that we're going to be solving these MIQPs. Those are difficult problems to solve in general. We cannot do things with billions of measurements for the time, okay? And we're comparing a bunch of algorithms here, basically various implementations of the lasso that have been out there for a long time. This figure here on the vertical axis shows the root mean square error of the different modeling techniques. Well, actually it shows the fraction of the models for which RMSE is below the numbers shown here on the horizontal axis. Okay, so you want an algorithm that's as far up and to the left as possible. As you can see, Alamo is doing very, very well. It finds very high quality models, much higher quality models than any of the other algorithms I'm comparing against. The price you have to pay here is it takes 4 or 5 orders of magnitude more for Alamo to run. Again, because Lasso does something very simple based on some quadratic programming stuff that's amazingly fast. But if you do have the time to build models, you will be able to build better models with Alamo, simpler and better. So I'm going to go now and, well, before I do that, before I go into an application, I'll briefly mention another capability that we have here, and that's to do what we call constraint regression. The literature refers to this as shape regression. And what it means is that I want to build a surface, I want to model my data, I want to build a model that also satisfies some physics, some chemistry, whatever information I might have on that front about the problem I'm trying to solve. So if I'm looking here to model a concentration, it better be non-negative. In which case, the red model here, even though it fits the data better, it predicts negative concentrations in certain parts of the domain. It's not a good model. I don't want to rely on that kind of model. How do I do this systematically? And can I even extrapolate and enforce constraints in parts of the domain where there's no way to take measurements because temperature is too high or pressure is too high? So I'm showing here an example in terms of the classical least squares regression that says I have a bunch of measurements, I have 2 regression coefficients, I have a model that I'm trying to build, and I would like to impose some constraints on that model. An easy constraint regression problem is to do standard least squares with the addition of some linear constraints on the regression coefficients. It's an easy problem. It's the same complexity as the unconstrained problem. But that's not the problem I'm interested in. I'm interested in imposing a constraint on the response surface itself, not on the coefficients. The coefficients don't mean much to me in general. So the problem I want to solve is least squares subject to the additional constraint that my response surface is everywhere non-negative. And this constraint here, now I have infinitely many constraints at every point in the domain. That makes the problem hard. But we can solve this with global optimization technology. It comes down to a semi-infinite optimization problem that can be systematically approached through cutting planes. And of course, I'm going to be using Baron to solve that problem as well. So we can do that sort of stuff as well. So I'm going to take now all this and go into an application. Say, I have flue gas coming out of my power plant, contains CO2. I don't like CO2. I would like to collect it and put it into the ground. How much would that cost me in comparison to not taking any action? So here's a proposal to take the flue gas, run it through a series of adsorbers and desorbers, and I have to now design this plant consisting of a number of units in series, in parallel. I have to figure out the dimensions of all these units, size them, I have to figure out flow rates, and so on and so forth. So what we're going to do, we are going to go there, model each of these units using a simulator for chemical processes, and then rely on that simulator to collect measurements, use the measurements to build data, to collect data and build models, and then take the models and obtain a mixed and nonlinear programming model for this overall plant Okay, the MNLP will tell me how many of these, which of these to select, how large to make them, how to operate the plant, and so on and so forth. So here's an example of one of the units, one of the reactors in this context, one of the separators rather. I'm showing here, we have about 15 input variables, 15 output variables. We're trying to model lots of things in this context. So the model was developed at the DOE, and we were just utilizing to collect measurements. And here are some of the models coming out of Alamo. This first model says pressure drop, the difference between input and output pressures, is proportional to the length of the bed. Anyone who knows anything about basic engineering stuff, we understand that's very important, basic in this context. And you can analyze the other kinds of expressions we're getting here. The interesting thing with an interpretable machine learning technique like Alamo is you can look at the model. Unlike the neural network, you can look at this and say, okay, this makes sense. I know it makes sense from the physical point of view, or maybe it doesn't make sense, something went wrong. Let me go back and figure that out, okay? Here's a very interesting result here. Now, I'm showing here the different quantities that we modeled. Two things, model size, so this complexity of the surrogate model we ended up with, and quality of the model in terms of RMSE, normalized RMSE. The interesting thing here is we see we don't need very large models, and yet we get very accurate results. This is something I did not expect when we were, going into this. I didn't know what to expect rather. But nowadays, when my students or anybody else comes and says, "Oh, I just came up with this fancy neural network and I'm modeling the system," it is this figure that actually makes me give me a pause, because I don't know how often we actually need neural networks to model engineering applications. I suspect not very often. I suspect, yes, in some imaging applications, we need those recurrent convolutionary neural networks, but in chemistry, physics, chemical engineering, mechanical engineering, I would be very surprised if there are cases in which I need a very detailed, a very complex neural network. We are finding that simple quadratic models often do the job, and we are publishing papers again and again demonstrating this. We just had a recent paper in your journal demonstrating this in the context of a leaching process for critical minerals. You don't need complex models oftentimes. A sparse quadratic is all you need, and you can actually interpret it. You can look at it, make sure it's accurate. Okay, so at the end, this is the optimal solution to this specific CO2 capsule problem. And in case you care about the adder to electricity is of the order of 30%. We did this for a specific adsorbent that had been invented at the DOE. We analyzed the plant for that specific separation system. And then at the end of the day, the question is, are you willing to pay 30% more for your electricity to treat CO2? Okay, but we were able to basically figure everything out by doing model building from data and then utilizing algebraic MNLP to solve this problem. So now going to the last problem, the third problem, that says, hey, I have a black box. That's all I have. I don't have any physics I can exploit. What can I do to optimize? And of course, there are many applications. Engineers have very complex models, PDs and the likes. They have key performance indicators they want to optimize, very complex set of differential equations. You don't have any algebraic solutions typically. Everybody's talking about machine learning nowadays. The enabling technology there is these graphics processing units. They come with a number of interesting parameters, like how many blocks, how do I go about arranging all those thousands of threads? Those threads must be arranged in terms of blocks. And the question is, one of the questions is, how many threads should I put per block? How many blocks do I run? Those are things that you often have to experiment with. And there's no way to build a model for the performance of the hardware. You have to experiment with that kind of stuff. Even in the context of a compiler, there's many options, and you have to play with those options to figure out what works best for your application. So if I want to optimize performance of any of these things, any of these contexts, I have to rely on measurements and nothing more than that. Okay, that's black box. Not a new problem. It's been out there for a long time, and many algorithms have been devised for it. You might be familiar with, I don't know, simulated annealing, for instance, or genetic algorithms. They're very popular out there. The first textbook in this field appeared relatively recently, telling you basically this field is relatively newer, not as mature as algebraic, MINLP, and the likes, but there's a great deal of interest, okay? So one of the first things we did, we said, okay, what kinds of algorithms are the most popular? So I have listed here some, and as you can see, the most popular algorithms are the stochastic algorithms. Those of the type that say, okay, I'm going to generate a random starting point and then do local search and then another random starting point, and I keep on going, for instance. Those are the most popular. In fact, even Facebook, when they came up with a library recently, they also rely on the same kinds of algorithms, stochastic algorithms. And by the way, Facebook, they have lots of parameter tuning problems. That's why they care about optimization on top of black boxes. Okay, it's not just Facebook, Google, everybody, every big AI company nowadays who wants to solve problems of this nature. So then the question is, which of these algorithms work the best? When we started, we collected a bunch of problems, over 500, a bunch of solvers, 22. Some of the problems here that we collected are convex, others are not. Some are smooth, others are not. As you can see, the dimensions here are not very large. You might have noticed from my MINLP slide, I think I had some averages there, maybe. We were able to solve problems with thousands of variables, thousands of constraints. Here, the state of the art is in the order of a few dozens, maybe hundreds. It's not beyond that. We put a limit on how many calls to the black box we were allowed to make. And we give a solver a problem, we give a problem to a solver if the solver comes close to a global optimum. How do they find the global optimal solutions? Well, I know these problems that I fit in there. They are available to me in algebraic format, so I can run them through Baron and get the global solution. And then the question is, if I treat them as black boxes, can I actually solve them with some algorithm? Mm-hmm. And what you see here on this figure, on the horizontal axis is problem size, on the vertical axis is fraction of problems solved by the solvers. If the problem is small with a couple of variables, we have very high success. The very moment we go to, say, a dozen variables, success drops significantly, and you go to larger problems and success keeps going down. So I view these numbers basically as what's the probability that any one of these algorithms is going to solve my problem, and that probability clearly goes down as I have more and more degrees of freedom. The interesting thing here, you don't see any of those stochastic algorithms coming up on top. The kinds of algorithms, MCS and direct, they're of the branch and bound type, although because I cannot bound, it's branch and bound without a bound in a clever way, okay? So in particular, I want to talk a little bit about this direct algorithm because I think that's a very interesting algorithm for black box optimization. And it was derived, I think Jones was at GM. He was very interested in optimizing on top of simulators. So the algorithm he came up with, here is shown in 2D. You have a set space in this box, takes a measurement in the center of the box, and then he will trisect the box, and then take two more measurements, the red points, again in the centers of those two boxes. The reason he's trisecting here is he's trying to save in terms of number of function evaluations. I don't have to take another measurement over there. I took that measurement in the first iteration. Yeah. And then he's saying, okay, what do I do next? He's going to pick up a box. I have three boxes here. He's going to pick up a box to subdivide. So if you pick up this box here, for instance, you can subdivide it, let's say in the horizontal direction. And again, he's trisecting and keeps on going, trisecting all the time, adding more measurements and continues. Of course, there are questions here, how do I go about which box do I pick? One simple answer is pick the box that's most promising, is the best measurement. Another answer could be, pick the largest box because we haven't really explored that box a whole lot. The interesting thing that I feel Jones came up with was a way to do this selection of boxes using some Lipschitz continuity assumption without actually requiring us to have the Lipschitz constant. And that was, I think, is very powerful. What I don't like, though, about this algorithm is this trisection and how we go about partitioning the set space and then taking measurements. This is not, doesn't have any connection to a lab, the way we would take measurements in a lab. You go to a chemistry lab or a materials lab, you're not going to run a single measurement. You're going to run a bunch of measurements if you fire up that machine. Pace to collect more measurements. The other thing is, I'm not going to be able to take measurements at exact points. There might be somewhere in the vicinity. I might come close. So these are issues that I'd like to overcome, make these kinds of algorithms work in a better way in the context of an actual experimental setup. So we're going to be using this, what we call BAM. This is branch and model. The previous algorithm, Baron, branch and reduce, or branch and bound. But now I'm going to be doing branch and model. I cannot bound anymore unless I have a Lipschitz constant, which I'm not going to assume. Instead, I'm going to be taking measurements, using them to build local surrogate models, and using those to guide the search. Okay? So I'm going to start. I'm showing here for a specific, it's a classic optimization problem, the Camel 6 problem. It's a 2D problem. There's two global minima shown here in pink, the pink triangles. Take a bunch of measurements any way you want. Might be through classical industrial engineering, space filling designs. Okay? So let's say these are the measurements in gray. At this point, what I'm going to do is I want to somehow partition the set space and use a branch and bound type of algorithm, but I don't want to do it in an arbitrary manner. Instead, what I'm going to do is I'm going to use the points here, and I'm going to draw boxes around them. So say I have these three measurements. I'm going to project them all on the coordinate axis. And then I'm going to look at all the consecutive projections and pick up the largest distance between two consecutive points. In this case, it's between these 2 points, and I'm now going to bisect that interval. This is going to introduce a partition element in my branch and bound, a smaller box. And I will then repeat this process on all remaining boxes where I have more than 1 point left. And you can show that it takes a finite number of steps until eventually you can separate all the points and you can draw a box around each and every point in the set of measurements. So that's what I get now for this problem. I started with 35 some measurements. I have 35 or so boxes. But I'm not forcing the algorithm to pick measurements in boxes that are arbitrary in some sense. Instead, I want to fit the boxes around the measurements in the hope that the measurements will be proper, a good representation of what's happening in each of these boxes. So now the question here is, which box do I choose to pursue further? I'm going to use this concept. I think this is what Jones was doing based on this Lipschitz constant. Assuming you have the Lipschitz constant, look at the box. I have a measurement. I have the diameter of the box. If only I had the Lipschitz constant available, this expression is now a lower bound for the optimal solution in that box. I don't want to pick a box unless its lower bound is at least as good as the lower bound for all the other boxes. In this expression, the only unknown is the Lipschitz constant. I can therefore rearrange, and if I find out that there's no positive constant for which this is satisfied, I know this box is not promising in this context. So that's what I'm going to use, and I think that's what Jones was using, although his geometrical arguments are beyond me. I don't understand them, but I think that's what he was doing. Yeah. The cool thing here is if you look at these 35 some boxes, only the four boxes here shown in red are potentially optimal based on this Lipschitz argument, this Lipschitzian argument. So I don't need to worry about all those 35 boxes. I only need to focus on these 4 boxes here and pursue them further. And what I'm going to do now is I'm going to look at each of these boxes, the potentially optimal ones. I'm going to look at all the adjacent boxes as well, use the measurements in the adjacent boxes to build models that are local for each of the potential optimal boxes. And then as I have those models, of course, will be obtained by Alamo. They will be simple. Typically, sparse quadratics is all we need. And then I'm going to rely on Baron to solve those models and help now guide the search. So what is cool here now is when you see the green points here, these are the optimal solutions for those surrogate models. 2 of them are pretty close already to a global optimum for this particular example. So we're able to come very, very close in just one iteration of this kind of algorithm. Yeah. But the bottom line is, I take the measurements, fit boxes, I look at adjacent boxes, build local models with Alamo, then optimize them with Baron. And now the green points is where I'm going to take more measurements. Or one of those green points I will select. I will also look at large boxes occasionally, pick up the largest and therefore more unexplored, take another measurement, let's say in the center of that box, and add that to the solution set and the set of measurements and keep on going through this process. The other thing we do here is every now and then we will fire up a local search algorithm. We don't want to be doing that too often. We want to decide when it's time to actually do a local search. And we're going to rely on another classic ML algorithm called dbScan. Don't want to go through details, so I'm going to say is it's a clustering type of algorithm that basically allows me to figure out when I have measurements that are pointing at a Bayesian, a local optimum, and it makes sense in that context to actually do local search. So same setting, same test of set problems, just comparing against the best algorithms that I found in the previous study and finding that BAM is actually solving more problems than any other algorithm that we have available. For low dimensional problems, it doesn't really matter what algorithm you solve, all of them work very well. It is as the dimensions increase that BAM is getting better and better than the competition. Here's the previous figure I showed you earlier, fractional problem solved. If I now put BAM in there, we're basically able to do a little better for problems around, with 30 degrees of freedom or so. Clearly, there's more that need to be done in this context. Here's an application I want to end up with. This is what motivated me to look into developing BAM. This is for the design of photovoltaic devices. We're doing everything in a lab. We're making devices. So it's a perovskite that has multiple layers. There's a number of things that can be optimized in that context. We have a collaborator who, when we started, was designing devices that had about close to 20% efficiency. The first thing we did in 2D, we optimized these 2 quantities here, basically the way we are making the device. And we saw a little bit of benefit by doing black box optimization in 2D. Then we went to 4D and we saw significant benefit in this context. And now we are somewhere at 6D and we're seeing even a bit more benefit. Up until, I want to say 4 months ago, this was the it tied up the world record for photovoltaics for this particular type of perovskite. 4 months ago, another paper has come out that's now closer to 26% in terms of efficiency. But I'm still optimistic because we are not even fully optimized here in 6D. And I know we can go to at least 30D, maybe even 100 dimensions and make more progress in this context. When we started, BAM was not available, so I was using Snopfit out of Neumeyer's lab in Vienna. All right. Yeah, and all this is in the lab. This is my students' figures, basically. I'm now partly an experimentalist. I'm not just doing theorems and coding. Yeah. All right, so just to wrap things up, I talked about 3 problems. MI-NLP, this is the state of the art. As I said, I cannot predict which solver is going to end up being ahead at the end, 5-10 years from now. But I can predict for sure that we will get closer to 100%. The community is working hard on these problems, and we will have better MI-NLP codes pretty quickly. The cool thing is that MI-NLP is serving as a technology to do interpretable ML. I talked about Alamo, other things we're doing in the context of symbolic regression. We're designing these trees in an optimal fashion. We're able to come up with nested non-linearity in the surrogate models. That's a step up from Alamo. But what I'm mostly excited about is potential applications in the context of going into the lab, optimizing devices and the likes with technology that basically relies on optimization and machine learning in a synchronized way. That's all for the day.